There is a clock ticking somewhere above you right now. Not in your room, not in your building, but 20,000 kilometers overhead, circling the Earth twice each day. This clock, aboard a GPS satellite, experiences time differently than you do. Not metaphorically, not approximately. Genuinely, measurably, physically different. If you could place an identical clock beside yours right now and another aboard that satellite and leave them running for a single day, the satellite clock would gain about 38 microseconds. 38 millionths of a second. A difference so small it seems to dissolve into irrelevance. Yet, without accounting for this difference, the blue dot showing your location on a map would drift off course by 10 kilometers every day. Within minutes, the entire GPS system would become unusable. This is not a story about broken clocks or measurement errors. The clocks work perfectly. Time itself flows at different rates depending on where you are and how fast you're moving. Stand on a mountain peak and you age faster than someone in the valley below. Travel in an airplane and you age more slowly than someone on the ground. Journey to the center of the Earth and time itself slows down compared to the surface. These aren't thought experiments or mathematical abstractions. They're verified facts about the universe we inhabit. The implications ripple outward in ways both profound and strange. Earth's iron core, which formed billions of years ago alongside the crust, is nevertheless 2.5 years younger than the surface. Not because it formed later, but because time has moved more slowly there, deeper in Earth's gravitational field, accumulating a deficit of years across the planet's history. A clock on Mount Everest's summit would be 39 hours ahead of a clock at sea level if both had been ticking since Earth's formation. The difference between your head and your feet is too small to notice in a human lifetime, yet it exists, persistent and real. We're going to explore why this happens. Not through complex equations or abstract theory, but by following the logic that led Einstein to one of the most beautiful insights in physics, that space and time are not the fixed stage upon which events unfold, but part of the performance itself, shaped by mass and energy, curved and warped and malleable. This will be a slow journey. There's no urgency here, no countdown, no race against revelation. We'll move through concepts one layer at a time, building understanding gradually, letting each idea settle before adding the next. Some of what we discuss will feel counterintuitive. Time that flows at different speeds, space that curves, gravity that isn't a force at all, but a consequence of geometry. These concepts resist quick comprehension because they describe a reality hidden from everyday experience. But they are comprehensible. Given patience and careful thought, the mystery begins to resolve. Not into something less wonderful, but into something more precisely wonderful, a universe stranger and more elegant than the one our intuitions suggest. So settle in, let your mind quiet. We're about to discover why time moves slower in space but faster on mountains, and in doing so, glimpse one of nature's most profound truths. Before we can understand how time behaves differently in different places, we need to examine what time actually is. This isn't a philosophical question, though philosophers have certainly wrestled with it. For our purposes, time is what clocks measure. This definition sounds circular until you realize it's profoundly practical. A clock is any system that undergoes regular, periodic change. The swing of a pendulum, the vibration of a quartz crystal, the oscillation of electromagnetic radiation absorbed and emitted by atoms, the decay of radioactive isotopes, the biological rhythms of cells dividing, neurons firing, hearts beating. All of these are clocks, each measuring time through cyclical processes. The best clocks are the most regular ones. A pendulum clock loses accuracy when temperature changes affect the metal's length. A quartz watch drifts as the crystal ages. But atomic clocks, which count the oscillations of light absorbed by cesium or strontium atoms, achieve extraordinary precision. The most accurate atomic clocks would lose only 1 second every 39 billion years, 3 times the current age of the universe. When we say time passes, what we really mean is that these cyclical processes continue. Cesium atoms oscillate, hearts beat, planets orbit, particles decay. The rate at which these processes occur relative to each other defines what we experience as the flow of time. In everyday life, we assume this rate is universal. A second is a second, whether you're standing still or moving, whether you're at sea level or on a mountain, whether you're on Earth or Mars. This assumption feels self-evident. How could time itself change? Time is the thing against which change is measured. It's the background, the stage, the fixed reference. Isaac Newton formalized this intuition in the 17th century. In his Principia Mathematica, Newton wrote that absolute, true, and mathematical time flows equably without relation to anything external. Time, in Newton's framework, was a cosmic metronome, ticking uniformly throughout the universe. An event that occurred at a specific moment occurred at that moment for all observers, everywhere, regardless of their motion or position. This framework worked magnificently for centuries. It predicted planetary orbits, explained tides, guided navigation, and formed the foundation for all of physics and engineering. The assumption of universal time was tested countless times and never found wanting, until the late 19th century when physicists began studying light. Light presented a puzzle. Experiments by Albert Michelson and Edward Morley in 1887 demonstrated that light travels at the same speed regardless of the observer's motion. This seems impossible at first. If you're driving 60 kilometers per hour and throw a ball forward at 20 kilometers per hour, the ball moves at 80 kilometers per hour relative to the ground. Velocities add. But light doesn't work this way. Shine a flashlight while moving, and the light travels at the same speed it would if you were standing still. Shine a light from a spaceship moving at 99% of light speed, and the light still travels at light speed relative to both you and a stationary observer. This constancy of light's speed seemed to violate common sense. How could light always travel at the same speed regardless of the motion of its source or observer? Something had to give. Either the measurements were wrong, or something fundamental about our understanding of space and time needed revision. In 1905, a 26-year-old patent clerk named Albert Einstein published a paper that resolved the contradiction. If light always travels at the same speed for all observers, Einstein reasoned, then time itself must be flexible. What we call simultaneous is not absolute, but depends on the observer's motion. Time is not a universal cosmic clock, but a local phenomenon, experienced differently by observers in relative motion. This was special relativity, and it revealed that time is not what we thought it was. Time is not separate from space. They form a unified structure called space-time, and the rate at which time passes, what we might call the speed of time, depends on motion through space. But motion wasn't the whole story. 10 years later, Einstein extended his theory to include gravity. And this extension revealed something even more surprising, that gravity itself affects the flow of time. Not through some mysterious force acting on clocks, but through the structure of space-time itself. To understand this, we need to follow Einstein's reasoning through what he called the equivalence principle, the insight that unlocked general relativity and revealed why time moves at different rates in different gravitational fields. In 1907, 2 years after publishing Special Relativity, Einstein was working at the patent office in Bern when he had what he later called the happiest thought of my life. He imagined a person falling from the roof of a house. During the fall, the person would feel weightless. They wouldn't feel gravity at all. In the person's reference frame, gravity would, in effect, not exist. This seems like a simple observation, but Einstein recognized its profound implication. There is no local experiment that can distinguish between free fall in a gravitational field and floating in empty space far from any mass. Both situations feel identical. Weightlessness in orbit and weightlessness in deep space are, in terms of local physics, the same. Einstein called this the equivalence principle, and he used it to explore gravity in a new way. If free fall eliminates the local effects of gravity, then perhaps the inverse is also true. Acceleration might create effects identical to gravity. Imagine you're in an elevator in deep space, far from any planet or star. There's no gravity. You float weightlessly. Now imagine the elevator begins accelerating upward at 9.8 meters per second squared. The same rate objects accelerate when falling on Earth. Suddenly, the elevator floor pushes against your feet with a force you interpret as weight. Drop an object and it falls toward the floor, accelerating at 9.8 meters per second squared. Every experiment you perform in this accelerating elevator gives the same results as experiments performed in a stationary elevator on Earth's surface. You feel weight. Objects fall. A ball thrown horizontally follows a curved path toward the floor. There is no way to tell, through local experiments, whether you're in a gravitational field or accelerating through empty space. This equivalence seemed too exact to be coincidence. Einstein reasoned that acceleration and gravity must be fundamentally the same phenomenon, viewed from different perspectives. An accelerating reference frame and a gravitational field are not merely similar, they are equivalent. This insight had immediate consequences for time. To see why, imagine that same elevator in space, accelerating upward. Place a clock at the floor and another at the ceiling. Now imagine a pulse of light emitted from the floor toward the ceiling. Light travels at a fixed speed, so the pulse takes a brief moment to traverse the elevator's height. During that moment, the elevator continues accelerating. By the time the light reaches the ceiling, the elevator is moving faster than when the light was emitted. From the perspective of someone at the ceiling, the light appears to be moving slightly slower than it would if the elevator weren't accelerating, not because the light actually slows down, but because the ceiling is moving away from the arriving light pulse. But wait, light always travels at the same speed in any local reference frame. This is a fundamental postulate of relativity. So how can the light appear to arrive with a different frequency at the ceiling than it was emitted with at the floor? The answer is that time itself must be running at different rates at the floor and ceiling. The clock at the floor, where the light was emitted, must be ticking more slowly than the clock at the ceiling, where the light arrives. Only if time passes more slowly at the floor can the light maintain its constant speed while appearing to change frequency. Now apply the equivalence principle. If this happens in an accelerating elevator, it must also happen in a gravitational field. A clock placed at the floor of a building on Earth must tick more slowly than a clock placed at the roof. Time itself flows at different rates at different heights in a gravitational field. This prediction seemed bizarre. Time had always been assumed universal and absolute. Now Einstein was suggesting that gravity affects not just the motion of objects, but the rate of time itself. A clock in a stronger gravitational field, closer to a massive object, runs more slowly than a clock in a weaker field. The effect is tiny on Earth. The difference between a clock at sea level and one at the top of a building is measured in billionths of a second per day. But tiny doesn't mean negligible, it means real. And if the theory was correct, it should be detectable with sufficiently precise measurements. The equivalence principle made another prediction. Light should also be affected by gravity, not because light has mass in the conventional sense, but because light carries energy, and in relativity, energy and mass are equivalent. If gravity affects time, and time affects the frequency of light, then light moving through a gravitational field should change its energy and frequency, what physicists call a gravitational redshift. Einstein developed these ideas over several years, culminating in the complete theory of general relativity in 1915. The theory described gravity not as a force, but as a consequence of space-time curvature. Massive objects warp the fabric of space-time itself, and what we experience as gravity is simply matter following the straightest possible paths through this curved geometry. But before we explore space-time curvature in detail, we need to understand the other way time can slow down: through motion. This brings us to special relativity and the phenomenon of velocity-based time dilation. Special relativity reveals that moving clocks tick more slowly than stationary ones. This isn't an illusion or measurement artifact. Time genuinely passes more slowly for objects in motion relative to a stationary observer. The key insight is that the speed of light is constant in all reference frames. No matter how fast you're moving when you measure light's speed, you always get the same result: approximately 299,792,458 meters per second. This constancy is experimentally verified and forms a cornerstone of modern physics. But if light speed is constant, something else must vary. That something is time itself. Imagine a simple clock. Two mirrors facing each other with a pulse of light bouncing between them. Each time the light completes one round trip, the clock ticks. Now imagine this clock moving past you at high speed. From your perspective, the light follows a diagonal path. It bounces from the bottom mirror upward, but while the light is in transit, the clock moves forward. So the light doesn't travel straight up, it travels up and forward simultaneously, tracing a diagonal. On the return journey, the light travels down and forward, completing a zigzag path. This diagonal path is longer than the straight up and down path the light follows from the clock's own perspective. But light must travel at the same speed in both reference frames, yours and the clock's. The only way the light can cover a longer path at the same speed is if more time elapses. From your perspective, the moving clock ticks more slowly than an identical clock at rest beside you. A second on the moving clock corresponds to more than a second on your stationary clock. The moving clock is time dilated. The amount of dilation depends on velocity. The faster the clock moves, the more time slows down from your perspective. The relationship is described by a factor called gamma, which equals 1 divided by the square root of 1 minus velocity squared divided by the speed of light squared. At everyday speeds, gamma is very close to 1 and the time dilation is negligible. A car traveling at 100 kilometers per hour experiences time dilation of about 1 part in 100 trillion. You would need to drive for billions of years to accumulate even 1 extra second, But at higher speeds, the effect becomes dramatic. At 90% of light speed, gamma is about 2.3. A clock moving at this velocity ticks at about 43% the rate of a stationary clock. At 99% of light speed, gamma is about 7. The moving clock ticks at 1/7 the rate of a stationary clock. At speeds approaching light speed, time dilation becomes arbitrarily large. At light speed itself, time would stop completely. But nothing with mass can actually reach light speed. This isn't theoretical speculation. Time dilation from motion is measured routinely in particle accelerators. Muons, which are unstable particles produced when cosmic rays strike the upper atmosphere, normally decay in about 2 microseconds. But when created at 99.9% of light speed, they live much longer from our perspective. Long. Enough to reach Earth's surface despite being created 15 kilometers up. From the muon's perspective, it lives its normal 2 microseconds, but from our perspective, time dilation extends its lifetime by a factor of about 20. Time dilation also affects atomic clocks in aircraft. In 1971, physicists Joseph Hafele and Richard Keating flew atomic clocks around the world on commercial airliners, comparing them with clocks that remained on the ground. The flying clocks experienced time dilation due to their motion. When the flights were complete, the clocks showed exactly the time difference predicted by relativity, a difference measured in nanoseconds but entirely consistent with theory. The twin paradox illustrates time dilation's implications. Imagine twins, one of whom departs on a journey to a distant star at 95% of light speed, while the other remains on Earth. When the traveling twin returns, they've aged less than their earthbound sibling. From the traveling twin's perspective, time passes normally. They experience no sensation of time moving slowly. But upon reunion, their biological clocks, cells, metabolism, memories, show less elapsed time. This seems paradoxical because motion is relative. Can't we equally well say the Earth moved away from the spaceship? Why should one twin age less than the other? The resolution is that the situation isn't symmetric. The traveling twin undergoes acceleration when leaving Earth, decelerating at the distant star, accelerating to return, and decelerating upon arrival. The Earthbound twin remains in a single inertial reference frame throughout. Acceleration breaks the symmetry, and the mathematics of general relativity confirms that the traveling twin genuinely ages less. But motion-based time dilation is only half the story. Gravity causes time dilation too, and the two effects are independent. An object can experience time dilation from its velocity and additional time dilation from being in a gravitational field. For GPS satellites, both effects are important and they work in opposite directions. General relativity extends special relativity to include gravity. While special relativity describes how time slows down for moving observers, general relativity reveals that time also slows down in gravitational fields. The stronger the gravity, the slower time passes. This gravitational time dilation arises from space-time curvature. In Einstein's theory, massive objects don't exert a force called gravity. Instead, they curve the geometry of space-time itself. What we interpret as gravitational attraction is simply matter following the natural contours of curved space-time, moving along geodesics, the straightest possible paths through the curved geometry. But space-time has 4 dimensions, 3 of space and 1 of time. When mass curves space-time, it curves both space and time. Near a massive object, not only is space warped, but time itself runs more slowly compared to regions farther from the mass. The amount of time dilation depends on gravitational potential. Gravitational potential measures the amount of energy required to move an object from one location to another against gravity. At Earth's surface, the gravitational potential is lower than at high altitude because you must expend energy to climb upward against gravity. Lower gravitational potential means slower time. A clock at sea level, deep in Earth's gravitational well, ticks more slowly than a clock at the top of a mountain. The difference is proportional to the gravitational potential difference between the two locations. The relationship can be expressed approximately as the fractional change in time equals the change in gravitational potential divided by the speed of light squared. On Earth, this works out to about 11 billionths of a second per meter of altitude per day. Over the course of a year, a clock 1 meter higher than another gains about 4 microseconds. These numbers sound impossibly small. 4 microseconds per year per meter of height? This is far beyond human perception. You will never notice your head aging faster than your feet, yet the effect is real and has been measured with extraordinary precision. The most stringent tests involve atomic clocks. In 2010, physicists at the National Institute of Standards and Technology compared two optical atomic clocks separated by just 33 centimeters, about the length of a ruler. Even over this tiny distance, they detected gravitational time dilation. The higher clock ticked faster, exactly as Einstein's equations predicted. More recently, in 2024, physicists at Nebula used an optical lattice clock to measure gravitational time dilation over a distance of just 1 millimeter, about the thickness of a small coin. At this scale, the time difference is measured in parts per 10 to the 18th power, yet the measurement matched theory perfectly. These experiments confirm that gravitational time dilation is not merely a mathematical prediction. It's a measurable feature of reality. Time genuinely flows at different rates depending on your position in a gravitational field. The effect scales with gravitational strength. On the Sun, whose mass is about 330,000 times Earth's mass, the gravitational potential difference between the surface and far from the Sun is much larger than Earth's. A clock on the Sun's surface would run about 66 seconds slower per year compared to a clock in interstellar space. Over billions of years, this accumulates to significant differences. Near a black hole, where space-time curvature becomes extreme, time dilation reaches extraordinary levels. At the event horizon, the boundary beyond which nothing can escape, time dilation becomes infinite from the perspective of a distant observer. A clock approaching the event horizon would appear to slow down more and more, never quite reaching the horizon, frozen in time from the outside observer's viewpoint. From the clock's own perspective, time passes normally, and it crosses the horizon in finite time. But the outside observer would never see this happen. Gravitational time dilation means that clocks in orbit around Earth, where gravity is weaker, tick faster than clocks on the surface. A GPS satellite, orbiting at about 20,000 kilometers altitude, experiences weaker gravity than we do. From general relativity alone, its clock would gain about 45 microseconds per day compared to a clock on Earth's surface. But GPS satellites also move at about 14,000 kilometers per hour. This velocity causes special relativistic time dilation, making the satellite clocks lose about 7 microseconds per day. The net effect is a gain of about 38 microseconds per day. Without correcting for these combined effects, GPS positioning would accumulate errors of several kilometers per day. The system would be useless within minutes. The fact that GPS works demonstrates that both special and general relativistic time dilation are real, measurable, and must be accounted for in practical technology. This isn't an abstract correction applied in post-processing. The satellite clocks are deliberately set to tick at a different rate than ground clocks before launch. Each GPS satellite's clock is set to 10.2299999954 3 MHz rather than the standard 10.23 MHz. This frequency offset, built into the hardware, compensates for relativistic effects so that once in orbit, the satellite clocks appear to tick at the same rate as ground clocks. The precision required is extraordinary. GPS timing must be accurate to within about 17 nanoseconds to achieve positioning accuracy of about 5 meters. This means accounting for time dilation to 9 or 10 decimal places. Without relativity, the entire system collapses. The fact that billions of smartphones rely on relativistic corrections every day is perhaps the most widespread practical demonstration of general relativity's validity. You carry proof of Einstein's theory in your pocket. Before GPS satellites and optical atomic clocks, before high-precision tests of general relativity became routine, there was the Pound-Rebka experiment, the first laboratory measurement of gravitational time dilation on Earth. In 1959, physicists Robert Pound and Glenn Rebka at Harvard University designed an experiment to detect gravitational redshift, the frequency shift of light climbing against gravity. This shift is a direct consequence of gravitational time dilation. If time runs slower in a stronger gravitational field, then light emitted from a lower elevation should have a lower frequency when measured at higher elevation, because the emitting atom's clock was running slower. The challenge was enormous. The gravitational potential difference across any accessible height on Earth is tiny. The Harvard Physics Building's tower was about 22.6 meters tall. The predicted fractional frequency shift over this height was about 2.5 parts per 10 to the 15th power, 2.5 parts per quadrillion. To detect such a minute shift, Pound and Rebka needed a light source with an extraordinarily sharp, well-defined frequency. They used gamma rays emitted by iron-57 nuclei. These gamma rays have an energy of 14.4 keV and normally have a relatively narrow spectral line. But there was a problem. When an atom emits a photon, the atom recoils slightly like a gun recoiling when firing a bullet. This recoil shifts the photon's energy, smearing out the spectral line far more than the gravitational shift they were trying to measure. The solution came from a phenomenon discovered in 1958 by Rudolf Nussbauer. He found that when atoms are embedded in a solid crystal lattice, the recoil energy is absorbed by the entire crystal rather than just the emitting atom. Because the crystal contains countless atoms, the recoil effect becomes negligible. The photon is emitted with almost no energy loss, creating an extraordinarily sharp spectral line, sharp enough to detect gravitational effects. Pound and Rebka's experimental setup was elegantly simple in principle. They placed a source of gamma rays at either the top or bottom of the tower and a detector at the opposite end. The detector contained iron-57 atoms that could absorb gamma rays if the energy matched exactly. Any frequency shift would prevent absorption. To compensate for the gravitational shift and bring the gamma rays back into resonance, they mounted the source on a loudspeaker cone and vibrated it up and down. This motion created a Doppler shift, the same effect that makes a siren's pitch change as an ambulance passes you. By adjusting the speaker's velocity, they could precisely cancel out the gravitational shift, bringing the gamma rays into resonance with the absorber. The velocity needed to cancel the gravitational shift became a direct measurement of the shift itself. When the source and absorber were at different heights, the speaker had to move at a specific velocity to restore resonance. That velocity corresponded exactly to the Doppler shift that compensated for gravity's effect. The experiment was extraordinarily sensitive to systematic errors. Temperature variations between the source and absorber could shift the spectral lines by more than the gravitational effect. A 1 degree Celsius temperature difference caused a shift comparable to the predicted gravitational redshift. Pound and Rebka mounted thermocouples at both locations and meticulously corrected for temperature. They also reversed the positions of source and absorber, sometimes placing the source at the top and sometimes at the bottom. Gravitational. Redshift predicts that gamma rays traveling upward should lose energy, while gamma rays traveling downward should gain energy. By measuring both directions, they could separate the pure gravitational effect from other systematic influences. After months of careful measurement and analysis, Pound and Rebka published their results in 1960. They measured a frequency shift of about 2.56 parts per 10 to the 15th power, compared to Einstein's prediction of 2.46 parts per 10 to the 15th power. The agreement was within their experimental uncertainty of about 10%. Later refinements by Pound and Joseph Snyder improved the accuracy to about 1% by 1964. The Pound-Rebka experiment provided the first terrestrial verification of gravitational time dilation and opened an era of precision tests of general relativity. The experiment's beauty lay in its directness. It didn't measure time dilation on clocks explicitly. Instead, it measured the frequency shift of light, which is equivalent. Light's frequency is essentially a clock. Each oscillation of the electromagnetic wave is like a tick. If time runs slower in a gravitational field, the clock ticks slower and the light's frequency decreases. The Pound-Rebka experiment detected this decrease directly. Their work confirmed that Einstein's predictions weren't merely mathematical abstractions, but described real, measurable phenomena. Gravity does affect the passage of time. Clocks in stronger gravitational fields genuinely run slower than clocks in weaker fields. This wasn't an approximation or a limit case. It was a fundamental feature of how our universe operates. The experiment also demonstrated the power of the Mössbauer effect for precision measurements. This technique enabled detection of frequency shifts far smaller than previously possible, opening new avenues for testing fundamental physics. Mössbauer received the Nobel Prize in Modern Dissertation in 1961 for his discovery. The Pound-Rebka experiment remains one of the classic tests of general relativity taught in physics courses worldwide. It showed that extraordinary precision could achieve terrestrial tests of effects usually associated with cosmic scales. You don't need to observe distant stars or black holes to test Einstein's theory. A tower 22 meters tall is sufficient if your instruments are precise enough. The global positioning system is perhaps the most widespread practical application of relativity. Every smartphone that shows your location, every navigation system that guides you to a destination, every aircraft that knows its position over the ocean, all of these depend on relativistic corrections to function accurately. GPS consists of a constellation of 31 satellites orbiting Earth at an altitude of about 20,000 kilometers. Each satellite carries multiple atomic clocks and continuously broadcasts time signals. A GPS receiver on Earth picks up signals from at least 4 satellites and uses the arrival times to calculate its position through a process called trilateration. The basic principle is straightforward. Each satellite broadcasts a time-stamped signal. The receiver notes when each signal arrives and compares this to the broadcast time. Since radio signals travel at the speed of light, the time difference reveals the distance to each satellite. With distances to 4 satellites, the receiver can determine its 3-dimensional position plus the time offset of its own internal clock. For this to work, timing must be extraordinarily precise. Light travels about 30 centimeters per nanosecond. To achieve positioning accuracy of about 5 meters, the system must measure time to within about 17 nanoseconds. This requires atomic clocks with stability better than 1 part in 10 to the 13th. But atomic clocks in orbit don't keep the same time as atomic clocks on Earth's surface. 2 relativistic effects alter their rate: velocity-based time dilation from special relativity and gravitational time dilation from general relativity. The satellites orbit at about 3,874 meters per second, roughly 14,000 kilometers per hour. At this speed, special relativity predicts that moving clocks tick more slowly than stationary clocks. The Lorentz factor for this velocity yields a time dilation of about -7 microseconds per day. The orbital clock runs slow compared to a ground clock, but the satellites are also at higher altitude where Earth's gravitational field is weaker. General relativity predicts that clocks in weaker gravitational fields tick faster than clocks in stronger fields. At GPS orbital altitude, the gravitational time dilation effect is about +45 microseconds per day. The orbital clock runs fast compared to a ground clock. These 2 effects work in opposite directions. The velocity effect slows the satellite clock by 7 microseconds per day. The gravitational effect speeds it up by 45 microseconds per day. The net result is a gain of about 38 microseconds per day. 38 microseconds might not sound significant, but light travels 11,400 meters in that time. Without correction, a GPS receiver would accumulate position errors of over 11 kilometers per day. Within 2 minutes, the error would exceed the accuracy threshold for navigation. The system would be useless. Engineers knew this before launching the first GPS satellites. The relativistic corrections were built into the system from the beginning. Each satellite's atomic clock is intentionally set to tick at a slightly wrong frequency before launch. Instead of the standard 10.23 MHz, the clock is set to 10.229999954 MHz, a difference of about 4.5 parts per 10 to the 10th. This frequency offset compensates for the combined relativistic effects. Once in orbit, experiencing both velocity-based time dilation and gravitational time dilation, the satellite clock appears to tick at the correct rate from Earth's perspective. The hardware correction handles the average effect for circular orbits. But GPS orbits aren't perfectly circular. They're slightly elliptical, which means satellite velocity varies throughout each orbit. When farther from Earth, satellites move slower and experience weaker gravity. When closer to Earth, they move faster and experience stronger gravity. These variations cause periodic timing corrections that can't be handled by a fixed frequency offset. Additional corrections, calculated by the receiver using orbital information broadcast by each satellite, account for these variations. The receiver applies formulas from general relativity to adjust for the changing gravitational potential and velocity along each satellite's elliptical path. There's also the Sagnac effect, a relativistic consequence of Earth's rotation. GPS receivers are typically not inertial, they rotate with Earth. This rotation creates an apparent time delay difference for satellites in the eastern versus western sky. The Sagnac correction is on the order of hundreds of nanoseconds and must be included for accurate positioning. All of these relativistic effects, special relativistic velocity time dilation, general relativistic gravitational time dilation, orbit eccentricity corrections, and the Sagnac effect, are accounted for continuously by GPS systems. The fact that GPS achieves positioning accuracy of a few meters proves that these corrections are accurate. GPS is effectively a continuously operating relativity experiment. Billions of receivers worldwide depend every day on the correctness of Einstein's theories. If the relativistic corrections were wrong, GPS would fail immediately. The system's decades of successful operation constitute an ongoing verification of both special and general relativity. Some GPS satellites have been in orbit for over 20 years, accumulating relativistic time differences that have been verified against ground clocks whenever satellites undergo maintenance or replacement. The measurements consistently confirm the predicted effects to high precision. The satellite clocks themselves are marvels of engineering. Early GPS satellites used rubidium atomic clocks with stability around 1 part in 10 to the 12th. Modern satellites carry cesium clocks with even better long-term stability. Some newer satellites incorporate hydrogen matzah clocks, which offer superior short-term stability. These clocks experience the harsh environment of space, vacuum, radiation, temperature extremes, yet maintain their precision year after year. The accumulated data from GPS timekeeping has contributed to tests of relativity with unprecedented statistical power simply by virtue of the system's global scale and continuous operation. Navigation isn't GPS's only use. Many applications require precise time rather than position. Financial markets use GPS time to timestamp transactions. Power grids use it to synchronize generators. Telecommunications networks use it to coordinate data transmission. Scientific experiments use it for time-tagging observations. All of these applications depend on relativity being correct. In a sense, GPS has democratized relativity. What was once an esoteric theory tested by specialist physicists is now embedded in technology used by billions daily. You don't need to understand the mathematics of curved space-time to benefit from it. You simply press a button and the corrections happen automatically, translating Einstein's insights into turn-by-turn directions. The effect of altitude on time is one of the most accessible demonstrations of gravitational time dilation. You don't need satellites or particle accelerators. Simply comparing clocks at different heights on Earth reveals time flowing at different rates. For every meter of altitude you gain, time runs faster by about 11 billionths of a second per day. This is an extraordinarily small effect, but it accumulates. Climb 100 meters and time speeds up by about 1 microsecond per day. Climb to the cruising altitude of an airplane, about 10,000 meters, and time gains roughly 100 microseconds per day compared to sea level. Mount Everest's summit sits 8,848 meters above sea level. A clock on the summit experiences weaker gravity than a clock at sea level and therefore runs faster. The difference is about 100 microseconds per day, or about 37 milliseconds per year, but Earth formed about 4.5 billion years ago. Over that vast span, a clock on Everest would have gained about 39 hours compared to a clock at sea level, if both had been ticking since. Earth's formation. Everest's rocks are, in a sense, slightly older in experienced time than rocks at sea level, even though they formed at the same moment in history. This seems paradoxical. How can something be older if it formed at the same time? The resolution is that forming at the same time and having experienced the same elapsed time are different things. Simultaneity depends on reference frame. Everest's summit and sea level may have originated simultaneously in Earth's early history, but since then, they've experienced different amounts of proper time due to gravitational time dilation. The altitude effect has practical consequences. When comparing atomic clocks at different locations to establish international time standards, scientists must correct for altitude differences. A clock in Tokyo sits at approximately 6 meters above sea level. A clock in Paris is about 35 meters above sea level. A clock in Mexico City is over 2,000 meters above sea level. These altitude differences cause timing offsets that must be factored out when synchronizing world timekeeping. Modern experiments can detect altitude effects over remarkably small distances. In 2010, physicists compared optical clocks at the National Institute of Standards and Technology separated vertically by just 33 centimeters. They measured a time difference consistent with gravitational time dilation at the precision of 1 part in 10 to the 17th, equivalent to a clock that would gain or lose 1 second in about 3 billion years per meter of altitude. An experiment planned for 2025 will take this even further. Scientists at NIST and the University of Colorado will transport an optical atomic clock to the summit of Mount Blue Sky, a peak rising 4,348 meters west of Boulder, Colorado. They'll compare it to a nearly identical clock in the Boulder laboratory via fiber optic cable. This experiment will measure gravitational time dilation over the largest altitude difference achieved with optical clocks. The predicted time difference at this elevation is about 48 microseconds per day. Measuring this with modern optical clocks will test general relativity to unprecedented precision over terrestrial scales. Even your own body experiences this effect. Your head is typically a bit less than 2 meters above your feet. This height difference causes your head to age about 90 nanoseconds faster than your feet per year. Over a 70-year lifetime, your head will have aged about 6 microseconds more than your feet. 6 millionths of a second older, accumulated cell by cell, heartbeat by heartbeat. This is far too small to detect biologically. No medical instrument can measure such tiny aging differences. You will never notice it, never feel it, never see its effects in a mirror, yet it exists, as surely as the distance between your head and feet exists. The altitude effect scales linearly with height for small altitude changes where gravitational field strength is approximately constant. But for very large altitude differences, satellite orbits for example, the relationship becomes nonlinear because gravitational field strength decreases with distance from Earth's center according to an inverse square law. Calculations of gravitational time dilation generally use the concept of gravitational potential rather than field strength. Potential is the integral of field strength over distance. At Earth's surface, gravitational potential is approximately negative 63 million joules per kilogram. At GPS satellite altitude, it's approximately negative 43 million joules per kilogram. This 20 million joule per kilogram difference drives the time dilation between ground and orbit. The mathematics of time dilation can become complex for extended mass distributions or strong gravitational fields. Earth isn't a perfect sphere. It's an oblate, spheroid, slightly flattened at the poles. Earth's interior has varying density with the dense iron core, less dense mantle, and even less dense crust. Accurate time dilation calculations must account for these complexities. The preliminary reference Earth model provides a standard description of Earth's internal structure used for seismology and gravitational calculations. Using this model, physicists have calculated precisely how time flows at different depths within Earth, from the surface down to the center. These calculations reveal something remarkable. Earth's core is younger than its surface, not geologically, but in terms of elapsed proper time. Since formation, the core has experienced less elapsed time due to gravitational time dilation. We'll explore this in detail in the next section. The altitude effect isn't unique to Earth. Any massive body creates gravitational time dilation. On the Moon, with its lower mass and weaker gravity, a clock at high elevation would gain less time relative to low elevation compared to Earth. On Jupiter, with its enormous mass, the effect would be much stronger. Near a neutron star, where gravity is intense beyond comprehension, altitude effects become dramatic. A clock 1 kilometer above a neutron star's surface would gain minutes per hour compared to a surface clock. Near a black hole, approaching the event horizon, time dilation becomes so extreme that clocks appear to nearly stop from a distant observer's perspective. But you don't need exotic astrophysical objects to witness time dilation. You need only climb a mountain. With every step upward, away from Earth's center, you enter a region where time flows slightly faster. You won't feel the change, but atomic clocks confirm it. Time itself speeds up as you ascend. Deep beneath your feet, beneath kilometers of rock and metal, lies Earth's core, a sphere of iron and nickel heated to thousands of degrees, squeezed by pressures millions of times, atmospheric pressure at the surface. This core formed about 4.5 billion years ago, shortly after Earth itself coalesced from the solar nebula. The core and the crust are essentially the same age geologically, yet the core is younger. Not by a few seconds or minutes, but by about 2.5 years. This isn't because the core formed later. It formed at essentially the same time as the rest of Earth during planetary accretion and differentiation. Rather, the core is younger because time has moved more slowly there since formation. The core sits deeper in Earth's gravitational well, experiencing stronger gravity than the surface. Gravitational time dilation has caused clocks in the core to tick more slowly than clocks at the surface for the entire history of the planet. The effect per year is minuscule. At Earth's center, time runs slower by about 3/10 of a second per day compared to the surface. This is roughly 3 parts in 10 to the 14th. UA would need an extraordinarily precise clock to measure this over human timescales. But Earth is 4.5 billion years old. 4.5 billion years is approximately 1.6 times 10 to the 17th seconds. Multiplied by the time dilation factor, the accumulated difference is approximately 2.5 years. That's how much less proper time has elapsed at Earth's center compared to Earth's surface. This calculation was first popularized by physicist Richard Feynman in lectures delivered in the 1960s. However, Feynman suggested the age difference was only a day or two. The correct value is much larger, about 2.5 years. This discrepancy went unnoticed for decades because most physicists simply accepted Feynman's estimate without checking the mathematics. His scientific reputation made his statements seem authoritative. In 2016, physicists Ulrich Ugehøj, R.E. Michelson, and J. Fay published detailed calculations in the European Journal of Physics, correcting Feynman's estimate. They calculated Earth's gravitational potential at various depths using the preliminary reference Earth model, which describes how density and gravitational field vary with depth. The calculation requires integrating the gravitational potential from Earth's surface to its center. Earth's structure complicates this because density isn't uniform. The iron-nickel core is much denser than the silicate mantle, which is denser than the crust. Each layer contributes differently to the gravitational field experienced at lower depths. The result depends on whether you assume Earth is a uniform sphere or use a realistic density profile. For a uniform sphere of Earth's total mass and radius, the age difference is about 1.5 years. Using the realistic preliminary reference Earth model increases this to about 2.5 years due to the core's higher density creating stronger gravitational fields at depth. This means that material at Earth's center has experienced 2.5 fewer years of proper time than material at Earth's surface. Every physical process, radioactive decay, thermal motion, quantum fluctuations, has undergone 2.5 fewer years' worth of evolution in the core compared to the crust. For perspective, 2.5 years is a tiny fraction of Earth's age, about 5 parts in 10 to the 10th, or 50 parts per billion. It's negligible geologically. It doesn't affect our understanding of Earth's formation or evolution. The core and crust are still the same age in any meaningful sense. But the fact that a difference exists at all illustrates the profound nature of time dilation. Time is not a universal backdrop ticking uniformly everywhere. It's a local phenomenon, flowing at different rates in different gravitational environments. The deeper you are in a gravitational well, the slower your clock ticks relative to clocks far from mass. The core's reduced age is unmeasurable directly. We can't place a clock at Earth's center and retrieve it for comparison. The calculation relies entirely on general relativity's predictions. But general relativity has passed every experimental test, so we have strong confidence the prediction is accurate. For the Sun, the effect is much more dramatic. The Sun's mass is about 330,000 times Earth's mass, and its gravitational potential difference between surface and center is correspondingly larger. Using the solar structure model, physicists calculate that the Sun's core is about 40,000 years younger than its surface. 40,000 years out of the Sun's 4.6 billion year age, roughly 1 part in 115,000. Still a small fraction, but substantial enough to be conceptually striking. The nuclear reactions powering the Sun, occurring deep in the core where hydrogen fuses to helium, have elapsed less time than processes in the Sun's outer layers. 4. Neutron stars, with their extreme density and gravity, the effect becomes even larger. A neutron star's surface can be years or centuries younger than exterior regions just a few kilometers away, depending on the star's mass. Inside a black hole, the time dilation becomes infinite at the event horizon from an external observer's perspective, though from an infalling observer's perspective, time passes normally. The Earth's core age difference is a vivid illustration of general relativity's predictions about time. Time genuinely flows at different rates in different locations. Not metaphorically, not approximately, but genuinely. A clock at the center of Earth would tick measurably slower than a clock at the surface if we could place them there and compare. This is part of what makes general relativity conceptually radical. We think of time as the universal stage on which events occur. But relativity reveals that time is part of the performance, shaped by mass and energy, variable, across space. There is no universal now extending throughout the cosmos. There are only local times, specific to particular locations and reference frames. Earth's core hasn't experienced as many seconds, as many heartbeats, as many oscillations of its atoms as the surface has. It is, in a real physical sense, younger by 2.5 years. Not because it formed later, but because it has lived less time. To truly understand why time moves at different rates in different places, we need to grasp what Einstein meant by space-time curvature. This isn't mere metaphor. Space-time is a real geometric structure, and mass genuinely curves it. In Newtonian physics, space is three-dimensional and time is separate, a universal parameter that flows uniformly everywhere. Objects move through space as time advances. Gravity is a force exerted by massive objects, causing other objects to accelerate toward them. But special relativity revealed that space and time aren't separate. They're interwoven into a four-dimensional continuum called space-time. Events are specified by four coordinates, 3 spatial coordinates and 1 time coordinate. Moving through space means moving through space-time, tracing a path called a world line. In flat space-time, the space-time of special relativity, far from massive objects, world lines of unaccelerated objects are straight lines. Objects in uniform motion trace straight paths through four-dimensional space-time. But near massive objects, space-time isn't flat, it's curved. In Einstein's general relativity, mass and energy curve the geometry of space-time itself. The curvature affects how objects move and how time flows. Visualizing four-dimensional curvature is impossible. Our minds can't picture four spatial dimensions. But we can understand it through analogy. Imagine a two-dimensional surface like a rubber sheet stretched flat. This represents flat space. Now, place a heavy ball on the sheet. The sheet curves around the ball, forming a depression. In this analogy, the ball is a massive object like a planet or star. The curved sheet represents curved space around it. A smaller object rolling across the sheet will follow a curved path around the depression, not because the ball exerts a force, but because the sheet itself is curved. The small object simply follows the straightest available path on the curved surface. General relativity applies this idea to four-dimensional space-time. Massive objects create curvature in space-time. Other objects follow geodesics, the straightest possible paths through the curved geometry. What we interpret as gravitational attraction is simply objects following these natural paths through curved space-time. But space-time has four dimensions, and the curvature affects time as well as space. Near a massive object, the time dimension is compressed. Time runs more slowly. Moving away from the massive object, the time dimension stretches. Time runs more quickly. This is gravitational time dilation, understood geometrically. It's not that gravity exerts some mysterious force on clocks. Rather, the very structure of time is different at different locations in a gravitational field. Time isn't a separate entity that could flow uniformly. It's part of space-time, and space-time is curved. The mathematics of curved space-time uses tensors and differential geometry, concepts that require years of study to master. But the conceptual core is accessible. Mass warps the four-dimensional geometry of space-time, and this warping manifests as both gravitational attraction and time dilation. Einstein's field equations relate space-time curvature to the distribution of mass and energy. The equations are compact in modern notation, but contain enormous complexity. In full form, they're 10-coupled, nonlinear, partial differential equations. Solving them for realistic situations, like the gravitational field around a rotating star, requires sophisticated numerical techniques. But for simple cases, solutions exist. The Schwarzschild solution describes space-time around a non-rotating spherical mass like Earth or the Sun. It reveals exactly how time and space are curved, providing the formula for gravitational time dilation we've discussed. The Kerr solution describes spacetime around a rotating mass like a spinning black hole. Rotation adds complexity, creating frame-dragging effects where spacetime itself is pulled around with the rotating mass. These solutions aren't just mathematical curiosities. They make predictions that have been tested extensively. The Schwarzschild solution predicts how much starlight bends passing near the Sun, a prediction confirmed during solar eclipses beginning in 1919. It predicts the precession of Mercury's orbit, an anomaly that had puzzled astronomers for decades before Einstein's theory explained it perfectly. It predicts gravitational redshift, confirmed by the Pound-Repka experiment. The Kerr solution predicts frame dragging, which was measured by Gravity Probe B, a satellite that orbited Earth for 17 months, measuring how space-time is dragged by Earth's rotation. The measurements matched predictions to about 1% accuracy after years of careful analysis. These experimental confirmations tell us that space-time curvature isn't mathematical abstraction, it's physical reality. Space-time genuinely has geometric structure that is affected by mass and energy. The structure genuinely affects how objects move and how time flows. One consequence of curved space-time is that there's no unique way to define simultaneous across extended distances in a gravitational field. Two events that are simultaneous in one reference frame may not be simultaneous in another. Time is local, specific to particular world lines through curved space-time. Another consequence is gravitational waves, ripples in space-time curvature propagating at light speed. When massive objects accelerate like two black holes orbiting each other, they create disturbances in space-time curvature that spread outward as waves. These waves were predicted by Einstein in 1916 but seemed impossible to detect. In 2015, the Laser Interferometer Gravitational Wave Observatory detected gravitational waves from merging black holes over 1 billion light-years away. The detection confirmed Einstein's predictions in spectacular fashion, opening a new window for observing the universe. Gravitational waves are proof that space-time is dynamical. It's not a fixed background, but a physical entity that can oscillate and carry energy. The geometry of reality itself ripples. Understanding gravitational time dilation through space-time curvature makes the phenomenon less mysterious. Time doesn't slow down because of some force acting on clocks. Time slows down because the geometric structure of the time dimension is different in a gravitational field. Clocks simply measure this geometry. They're sensitive to the shape of space-time itself. This geometric view unifies gravity with the other aspects of space-time. Gravity isn't a separate force, but a manifestation of geometry. Mass and energy tell space-time how to curve. Space-time tells matter how to move. And the curvature of space-time includes the time dimension, causing time to flow at different rates in different locations. When you climb a mountain, you're moving to a region where space-time is curved differently. Not just the spatial dimensions, but the time dimension too. Time genuinely runs faster at higher altitude because the geometric structure of space-time is different there. The curvature is less extreme, the gravitational potential higher, and the rate of time's flow increases accordingly. Gravitational time dilation isn't limited to human-scale objects or Earth-based experiments. It's a universal phenomenon occurring at every scale, from subatomic particles to the most massive objects in the cosmos. At quantum scales, time dilation affects particle decay rates and atomic processes. An atomic nucleus at Earth's center experiences slightly less time than one at the surface, affecting its decay probability. Radioactive isotopes used for dating would yield slightly different ages depending on where in a gravitational field they spent their history, though the effect is far too small to measure with current techniques. Atomic clocks, the most precise timekeepers we've created, detect time dilation through the frequency of light absorbed by atoms. These clocks work by isolating single atoms or small collections of atoms and measuring the frequency of light they absorb when transitioning between energy levels. The transition frequency is extraordinarily stable, nature's most reliable periodic process. Modern optical atomic clocks achieve precision better than 1 part in 10 to the 18th power. This means they would lose or gain less than 1 second over the entire age of the universe, about 14 billion years. At this precision, gravitational time dilation becomes measurable over distances as small as a millimeter. For stars, time dilation affects their entire evolutionary timeline. The Sun's core, where nuclear fusion occurs, experiences stronger gravity than the surface. Over the Sun's lifetime of about 10 billion years, this creates an age difference of roughly 40,000 years between core and surface. Nuclear reactions in the core have proceeded through 40,000 fewer years of proper time than processes at the surface. For white dwarfs, the dense remnants of dead stars, gravity is much stronger and time dilation becomes more pronounced. A white dwarf's surface can be centuries younger than regions farther away. Neutron stars, even denser, have surface regions that are millennia younger than distant space. Black holes represent the extreme case. At the event horizon, time dilation becomes infinite from an external observer's perspective. A clock falling toward a black hole appears to slow down more and more, its ticking rate decreasing asymptotically, never quite reaching the horizon. From the clock's own perspective, time passes normally, and it crosses the horizon in finite, proper time. But external observers would never see this crossing occur. This creates a peculiar situation. From outside, nothing ever enters a black hole. Objects appear to freeze just above the horizon, gradually redshifting and fading into invisibility. Yet, from the infalling object's perspective, the crossing happens quickly and unremarkably, at least until tidal forces become extreme near the singularity. The universality of time dilation means it affects everything equally. Atomic clocks, biological processes, radioactive decay, light propagation, all experience time dilation identically. There's no reference process that ticks at a true rate. Time itself flows differently in different gravitational fields and at different velocities. This universality distinguishes time dilation from other relativistic effects. Length contraction, for instance, depends on the reference frame you choose, but time dilation, while also reference frame dependent, affects all processes uniformly within a given frame. At planetary scales, time dilation shapes the history of worlds. Mars, with its lower mass, has weaker gravity than Earth. A clock at Mars's surface runs faster than a similar clock at Earth's surface when both are compared to a clock in deep space. Over billions of years, Mars has experienced more proper time than Earth. Jupiter, much more massive, creates stronger time dilation. Its surface has experienced less proper time than Earth's surface since formation. The difference isn't large. Jupiter's core is only about 60 years younger than its surface, but it exists, woven into the planet's history. For planetary formation, time dilation affects chemical processes in young solar systems. Dust grains deep in a protoplanetary disk's gravitational well experience slightly less time than grains at the disk's edge. This doesn't significantly affect planet formation, but it demonstrates that even primordial processes occur against a backdrop of varying time flow. At galactic scales, time dilation becomes relevant near supermassive black holes. The black hole at the Milky Way's center, Sagittarius A18, has a mass of about 4 million solar masses. Stars orbiting close to it experience significant time dilation. A star in a tight orbit around Sagittarius A18 ages more slowly than stars farther away. This has consequences for stellar evolution. Close to the black hole, stars progress through their life cycles more slowly from our perspective. Nuclear fusion proceeds at the same rate from the star's own perspective, but less time elapses there compared to distant regions. For the most extreme black holes, supermassive black holes in active galactic nuclei with masses billions of times the Sun's, time dilation affects entire regions of space. Material in accretion disks spiraling toward these monsters experiences profound time dilation. Days on Earth correspond to hours or minutes in the disk's inner regions, depending on proximity to the event horizon. Quasars, powered by such supermassive black holes, show evidence of time dilation in their variability. Light curves from distant quasars appear stretched in time due to cosmological redshift, a consequence of the universe's expansion, which also affects time. Observations of quasar variability help astronomers understand black hole masses and accretion rates. Time dilation also affects gravitational waves. When two black holes merge, the final moments before collision occur in a region of extreme space-time curvature. Time dilation means the merger unfolds more slowly for external observers than for an observer hypothetically near the event. The gravitational waves we detect carry information about this warped space-time. From atoms to black holes, time dilation operates identically. It's not a correction applied to clocks. It's a fundamental feature of how time works in the presence of mass and energy. Einstein revealed that time isn't separate from space, and neither is separate from matter. They form an integrated structure, and that structure is curved by mass. This universality is both profound and strange. It means there's no absolute now extending across the cosmos. Time is local, specific to particular world lines through space-time. Your now and someone else's now at a different location or velocity are different moments in space-time, related by coordinate transformations but not identical. Yet despite this relativity of simultaneity, causality remains intact. Cause always precedes effect. No observer, regardless of their motion or position in a gravitational field, will ever see effects preceding causes. The structure of space-time ensures this, through its causal structure. The light cones that define which events can influence which other events. Time dilation reveals that the universe is stranger and more elegant than our intuitions suggest. Time flows at different rates, yet the laws of physics remain consistent. Clocks disagree, yet predictions remain accurate. Reality accommodates both the relativity of time and the universality of physical law. The detection of gravitational time dilation requires extraordinary precision. The effects are tiny on human scales, billionths of a second per day per meter of altitude on Earth. Measuring such minute differences pushes technology to its limits. The history of atomic clocks tracks humanity's increasing ability to measure time precisely. Early atomic clocks, developed in the 1940s and 50s, used cesium atoms and achieved precision of about 1 part in 10 to the 10th power, accurate to about 1 second every 300 years. By the 1970s, when Haffel and Keating flew atomic clocks around the world, Cesium clocks had improved to about 1 part in 10 to the 13th power, accurate to about 1 second every 300,000 years. This was barely sufficient to detect relativistic effects from airplane flights. Modern cesium fountain clocks, which are the basis for international time standards, achieve precision of about 1 part in 10 to the 16th power. These clocks would be accurate to about 1 second in 30 million years. GPS satellites use rubidium and cesium clocks with similar precision, but optical atomic clocks, developed over the past 2 decades, have surpassed cesium clocks dramatically. By using visible or ultraviolet light instead of microwave radiation, optical clocks achieve frequencies millions of times higher. Higher frequency means more oscillations per second, which translates to better precision. The best optical clocks now achieve precision better than 1 part in 10 to the 18th power. They would lose or gain less than 1 second over the entire 14 billion year age of the universe. At this precision, gravitational time dilation becomes measurable over remarkably small distances. In 2010, NIST physicists compared 2 aluminum-ion optical clocks separated by just 33 centimeters vertically. Even over this distance, they detected gravitational time dilation matching Einstein's predictions. The fractional frequency difference was about 4 parts in 10 to the 17th, extraordinarily small, yet clearly measurable. The experiment required extraordinary care. Temperature differences between the clocks had to be controlled to millikelvin precision. Vibrations had to be minimized. Electromagnetic fields had to be shielded. Any systematic error could swamp the tiny relativistic signal. More recently, in 2022, JILA researchers measured gravitational time dilation over just 1 millimeter using a single optical lattice clock containing about 100,000 strontium atoms. They compared the tick rate of atoms at the top of the cloud to atoms at the bottom, separated by 1 millimeter. The technique involved imaging the atoms with extreme precision to determine their positions, then comparing the frequency of light absorbed by upper versus lower atoms. The frequency difference revealed that lower atoms experienced slightly stronger gravity and therefore ticked slightly slower. This millimeter-scale measurement represents the smallest distance over which gravitational time dilation has been detected. It demonstrates that Einstein's theory holds even at scales approaching the realm where quantum mechanics dominates. The precision of these experiments is difficult to grasp intuitively. 1 part in 10 to the 18th means detecting a 1-second difference over a time span 3 times longer than the universe has existed. Or equivalently, detecting a frequency shift of 1 Hz. When the frequency itself is 10 to the 18th Hz, a quintillion oscillations per second. Achieving this requires isolating single atoms or small clouds of atoms, cooling them to microkelvin temperatures to minimize thermal motion, interrogating them with laser light of extraordinary stability, and averaging measurements over hours or days to reduce noise. The lasers used in optical clocks are themselves marvels. Their frequency must be stable to better than 1 part in 10 to the 16th, equivalent to maintaining a particular color of light so precisely that the wavelength doesn't vary by more than the diameter of a proton over a distance of 1 meter. This stability is achieved through complex feedback systems. The laser is locked to a reference cavity, a tube with mirrors at both ends, kept at constant temperature and isolated from vibrations. Light resonates inside the cavity, and any frequency drift in the laser causes the resonance to shift, generating an error signal that corrects the laser's frequency. But reference cavities are limited by thermal noise, random fluctuations in the cavity's length due to molecular motion. Even at room temperature, thermal noise limits cavity stability. Some advanced systems cool cavities to cryogenic temperatures to reduce this noise. The atoms themselves serve as the ultimate frequency reference. Each type of atom has characteristic transition frequencies determined by quantum mechanics. These frequencies are extraordinarily stable because they depend only on fundamental constants of nature. An atom of strontium-87 in Colorado absorbs light at exactly the same frequency as an atom of strontium-87 in Japan or on the Moon. By locking lasers to atomic transitions, scientists create frequency standards that don't drift over time and aren't affected by environmental conditions. The challenge is measuring the transition frequency with sufficient precision. This requires long interrogation times. The age, atoms must be isolated from perturbations, electromagnetic fields, blackbody radiation, collisions, so the transition can be probed without disturbance. Optical lattice clocks confine atoms in a periodic potential created by standing waves of light, holding them nearly motionless while lasers probe their transition. The atoms are typically cooled to microkelvin temperatures, millionths of a degree above absolute zero. At these temperatures, thermal motion is minimized, and the atom's quantum behavior becomes pronounced. They exist in superpositions of quantum states, enabling precision measurements through quantum interference. Measuring time dilation at millimeter scales with these clocks requires comparing the tick rates of atoms at slightly different heights. In the GILA experiment, imaging systems determine which atoms were at the top versus bottom of the cloud. The frequency of light absorbed by each group was measured separately. The frequency difference revealed gravitational time dilation. Lower atoms, in stronger gravity, absorbed light at a slightly lower frequency, a gravitational redshift. The magnitude of the shift matched Einstein's predictions precisely. These measurements serve multiple purposes beyond testing relativity. They enable fundamental physics experiments, such as searching for variations in fundamental constants or testing whether dark matter affects atomic transitions. They also have practical applications in geodesy, precise measurement of Earth's gravitational field. A network of optical clocks could map Earth's geoid, the surface of constant gravitational potential that corresponds to mean sea level. Traditional geodetic measurements use satellites and ground surveys, but optical clocks could provide complementary data with higher precision and time resolution. Such measurements could detect underground mass changes, magma movement before volcanic eruptions, water table variations, ice loss from glaciers. Clocks, separated by kilometers, could be compared via fiber optic links, measuring the gravitational potential difference between locations. This application remains mostly theoretical, but is being actively developed. Portable optical clocks are being designed for field deployment. Fiber optic networks for clock comparison are being extended. Within decades, gravitational cartography using atomic clocks may become routine. The progression from Hafele and Keating's airplane flights to millimeter-scale measurements spans 5 decades and represents roughly a million-fold improvement in precision. This exemplifies how technological progress enables increasingly stringent tests of fundamental physics, but precision alone isn't the goal. The goal is understanding. Each improvement in measurement capability reveals new facets of how nature operates. Time dilation, once an exotic prediction, is now measured routinely at scales ranging from satellites to millimeter-separated atoms. The measurements confirm that Einstein's theory isn't merely approximately correct. It's extraordinarily precise, holding at scales from planetary to subatomic. Every test strengthens confidence that general relativity accurately describes gravity and space-time. yet mysteries remain. General relativity and quantum mechanics, our two great theories of the 20th century, remain incompatible. Relativity describes gravity as space-time curvature, while quantum mechanics describes other forces through particle exchange. Attempts to reconcile them, quantum gravity theories, remain speculative. Some physicists hope that ultra-precise atomic clocks might reveal deviations from general relativity that hint at quantum gravitational effects. If gravity disrupts quantum coherence, or if time dilation behaves slightly differently at atomic scales than classical theory predicts, optical clocks might detect it. So far, no deviations have been found. General relativity continues to pass every test, but the search continues, driven by the conviction that understanding how gravity and quantum mechanics coexist is one of physics' great remaining challenges. Meanwhile, the practical applications of time dilation grow. GPS is just the beginning. Future navigation systems, whether satellite-based or using alternative technologies, will require even more precise timing. Quantum communication networks, which use entangled photons to transmit information securely, need synchronized clocks at different locations. As technology progresses, time dilation shifts from exotic theory to engineering constraint. Designers of precision systems must account for relativistic effects even on Earth's surface. The universe imposes these constraints. Technology must adapt. Time dilation isn't merely a curiosity for physicists. It affects technology we use daily and places fundamental limits on what's achievable. GPS is the most widespread example. Every smartphone relies on relativity to determine location. The system's architecture, satellites broadcasting time signals, receivers comparing arrival times, requires accounting for both gravitational and velocity-based time dilation. Without relativistic corrections, GPS would accumulate errors of about 10 kilometers per day. Within 2 minutes of turning on a GPS receiver, the position error would exceed the system's accuracy specification. Navigation would be impossible. Engineers building GPS knew this from the beginning. The system launched in the 1970s, decades after relativity was confirmed experimentally. Designers built corrections directly into the satellite clocks, setting their frequencies slightly wrong to compensate for time dilation. This integration of relativity into hardware is remarkable. The satellite clocks tick at the wrong rate on the ground. Only once in orbit, experiencing combined velocity and gravitational time dilation, do they tick at the correct rate from Earth's perspective. Additional corrections handle orbital eccentricity, Earth's rotation, and other effects. These are computed by receivers using broadcast orbital data. The mathematics of relativity is embedded in every GPS chip, executed countless times per second in billions of devices. GPS's success demonstrates that relativity is correct and that engineers can apply it reliably. The system has operated for decades, achieving positioning accuracy of a few meters globally. This wouldn't be possible if relativistic corrections were wrong. Beyond navigation, precise time synchronization matters for many technologies. Financial markets timestamp transactions to microsecond precision to establish sequence and prevent fraud. Power grids synchronize generators across vast distances to maintain stable frequency. Telecommunications networks coordinate data transmission. All these applications use GPS time for synchronization. Receivers at critical locations, stock exchanges, power plants, cell towers continuously update their clocks from GPS signals. This creates a distributed time standard accurate to nanoseconds worldwide. But GPS time isn't perfect. Signal delays from atmospheric effects introduce errors. Multipath. Signals bouncing off buildings before reaching receivers causes additional errors. For applications needing better than 10 nanosecond accuracy, GPS isn't sufficient. Future systems may use optical atomic clocks connected by fiber optic links. Optical fibers can carry time signals with picosecond precision over thousands of kilometers. Networks of clocks could provide timing orders of magnitude better than GPS. Europe is developing such a system called the European Optical Clock Network. It connects optical atomic clocks at national metrology institutes via dedicated fiber links, creating a continental time standard of extraordinary precision. Similar efforts are underway in the United States, Japan, and China. Eventually, a global optical clock network could replace GPS for the most demanding timing applications. Such networks must account for gravitational time dilation along the fiber routes. A fiber passing through mountainous terrain connects locations at different altitudes, experiencing different gravitational potentials. Time signals traveling the fiber must be corrected for the accumulated time dilation. This requires knowing the fiber's precise elevation profile. Surveying provides this, but optical clocks themselves offer an alternative. By comparing clocks at different locations, the gravitational potential difference can be measured directly. This reveals elevation differences without surveying. This technique, relativistic geodesy, inverts the usual problem. Instead of using known elevations to correct clocks, clocks reveal elevations. Preliminary experiments demonstrate its feasibility. Optical clocks separated by kilometers can measure height differences to centimeter precision. Applications extend beyond geodesy. Monitoring underground water levels, detecting tectonic motions, tracking ice sheet changes, all could benefit from clock-based measurements. The clocks reveal gravitational potential, which reflects mass distribution. A decrease in groundwater lowers the local gravitational potential, causing nearby clocks to tick faster. Magma rising beneath a volcano increases the potential, slowing clocks. Ice melting from a glacier reduces its mass, affecting the potential and clock rates. These effects are tiny, parts per 10 to the 16th or smaller. Only optical atomic clocks can detect them. But as these clocks become more portable and affordable, such applications may become practical. Time dilation also affects particle physics experiments. Particle accelerators like the Large Hadron Collider accelerate protons to 99.99999% of light speed. At these velocities, time dilation is extreme. Particles live much longer from our perspective than their intrinsic lifetime suggests. Muons, created in particle collisions, normally decay in about 2 microseconds. But at near light speed, time dilation extends their lifetime by factors of thousands or more. This allows muons to traverse the entire accelerator ring before decaying, something impossible without time dilation. Particle physics calculations routinely account for time dilation. Collision energies, detector timings, particle trajectories, all must be computed in the appropriate reference frame. Relativity is woven throughout the mathematics. Cosmic ray physics provides natural demonstrations. Muons created when cosmic rays strike the upper atmosphere at 15 kilometers altitude normally couldn't reach Earth's surface before decaying. But their near-light speed causes severe time dilation, extending their lifetime enough to reach the ground. From the muon's perspective, it lives only 2 microseconds. But distance contraction, the spatial counterpart of time dilation, makes the atmosphere appear compressed to just a few hundred meters thick. From the muon's reference frame, it easily traverses this distance in its brief lifetime. both descriptions are correct. Time dilation in our frame and distance contraction in the muon's frame describe the same phenomenon from different perspectives. This interplay between space and time is central to relativity. For space travel, time dilation becomes significant. A spacecraft traveling at 90% of light speed experiences time dilation by a factor of about 2.3. A journey lasting 10 years for travelers takes 23 years for people on Earth. At 99% of light speed, the factor increases to about 7. A 10-year journey for travelers takes 70 years on Earth. At 99.9%, the factor is about 22. A 10-year journey takes 220 years on Earth. This enables interstellar travel within human lifetimes, at least for the travelers. A trip to a star 50 light-years away at 99.99% of light speed would take about 50 years for Earth, but only about 2 years for travelers. The catch is energy. Accelerating to such speeds requires enormous energy, increasing with velocity. Reaching 99.99% of light speed needs energy about 70 times the spacecraft's rest mass. For a 1,000 kilogram spacecraft, this is about 70 trillion joules, equivalent to about 5 billion nuclear weapons. Current rocket technology is hopelessly inadequate. Even theoretical propulsion systems like nuclear pulse propulsion or antimatter rockets couldn't approach such speeds practically. Interstellar travel at relativistic speeds remains science fiction, limited by energy requirements rather than physical impossibility. But time dilation is real, measurable, and consequential for technology we use every day. From GPS to particle accelerators, from atomic clocks to cosmic rays, relativity shapes how the universe operates and how we interact with it. Einstein's insight that time is relative, not absolute, revolutionized physics and continues influencing technology a century later. The strange truth that clocks disagree depending on motion and gravity isn't a flaw or approximation. It's how time actually works. Einstein's theories of relativity are often portrayed as incomprehensibly complex, accessible only to mathematical physicists. The full mathematical treatment does require years of study, but the conceptual core is elegant and, with patience, understandable. Special relativity begins with two postulates. The laws of physics are the same in all inertial reference frames, and the speed of light is constant for all observers. These seem almost trivial, yet they overturn centuries of assumptions about absolute space and time. If light speed is constant, and you measure light from a moving source, how can you get the same speed as someone stationary? The only way is if your time and space measurements differ from theirs. Time must be relative to the observer. This leads directly to time dilation and length contraction. Moving clocks tick more slowly. Moving objects appear contracted in their direction of motion. Simultaneity becomes relative. Events simultaneous in one frame aren't simultaneous in another. These aren't optical illusions or measurement artifacts. They're genuine features of space-time. Time and space aren't separate, absolute backdrops, but interwoven into a four-dimensional structure that different observers slice differently. General relativity extends this by including acceleration and gravity. Einstein's key insight was the equivalence principle. Acceleration and gravity are locally indistinguishable. An accelerating rocket in space creates effects identical to a gravitational field. This suggested that gravity itself might be understood as a feature of space-time rather than a force. Einstein developed this idea into a geometric theory. Mass and energy curve space-time and objects follow geodesics, the straightest possible paths through the curved geometry. What we experience as gravity, the pull toward Earth, is actually the curvature of space-time making straight paths through space-time appear curved in space. We fall not because Earth pulls us, but because space-time's curvature directs our motion downward. This geometric perspective unifies space, time, and gravity into a single framework. The curvature affects both spatial paths and time's flow. Hence, gravitational time dilation. Deeper in a gravitational field, where space-time curvature is stronger, time flows more slowly. The beauty of this framework is its simplicity. One concept, space-time curvature, explains diverse phenomena: planetary orbits, light bending near the sun, gravitational time dilation, black holes, gravitational waves, the expansion of the universe. Einstein's field equations, which describe how mass-energy curves space-time, are compact. In modern notation, they're just 10 coupled differential equations. But these equations encode profound complexity. Solving them for realistic situations often requires numerical computation. Yet the physical content is clear. Mass and energy tell space-time how to curve. Space-time tells matter how to move. This reciprocal relationship creates dynamics: gravitational waves, collapsing stars, expanding universes, all from geometry. The theory makes precise, testable predictions. Light should bend near massive objects. Gravitational waves should propagate at light speed. Time should flow differently in different gravitational fields. Mercury's orbit should precess in a specific way. All these predictions have been confirmed experimentally. General relativity has passed every test for over a century. From solar system scales to cosmological scales, from weak fields to strong fields near black holes. The theory matches observations with extraordinary precision. Yet physicists know it's incomplete. General relativity treats space-time as a smooth continuum, but quantum mechanics suggests space and time may have discrete structure at the Planck scale, about 10 to the minus 35 meters. Reconciling continuous space-time with quantum discreteness is a central problem in theoretical physics. Additionally, general relativity predicts singularities, points where curvature becomes infinite, at black hole centers and the universe's beginning. Physicists suspect these singularities signal where the theory breaks down and quantum effects become essential. Quantum gravity, a theory combining general relativity and quantum mechanics, remains elusive. String theory, loop quantum gravity, and other approaches offer possibilities, but none is confirmed experimentally. The energies and scales where quantum gravitational effects become important are far beyond current experimental reach. Despite these unknowns, general relativity works magnificently within its domain. For astrophysics, cosmology, and precision measurements, it provides extraordinarily accurate predictions. GPS satellites, gravitational wave detectors, black hole imaging, all rely on general relativity's accuracy. The theory's longevity is remarkable. Published in 1915, it remains the best description of gravity we have. Most scientific theories get superseded within decades. General relativity has stood for over a century, its predictions consistently verified. This success reflects the theory's deep connection to nature's structure. Space-time curvature isn't an arbitrary mathematical construct. It's how gravity actually works. Mass genuinely warps geometry. Time genuinely flows differently in different locations. Einstein's vision that space and time form a unified, dynamic structure shaped by mass and energy revolutionized physics. But more than that, it revealed a universe far stranger and more beautiful than anyone had imagined. The strangeness is that time isn't what we thought. It's not a universal flow carrying all events forward at the same rate. It's local, malleable, dependent on circumstance. Your time and mine differ if we move differently or occupy different gravitational fields. The beauty is that despite this relativity, nature remains comprehensible. Physical laws don't change. Causality is preserved. Mathematics describes it all precisely. The universe accommodates both the relativity of time and the consistency of physical law. We've journeyed from GPS satellites circling overhead to the center of the Earth, from mountain peaks to black hole event horizons, following the strange but verified truth that time moves at different rates in different places. This isn't philosophy or metaphor. It's established physics, tested extensively, confirmed repeatedly, and applied routinely in technology. Atomic clocks separated by a meter detect it. GPS satellites require it. Particle accelerators observe it. The universe operates this way. Time flows slower in stronger gravitational fields, deeper in a gravitational well, closer to Earth's center near a massive star approaching a black hole. Clocks tick more slowly than clocks farther away. Earth's core is 2.5 years younger than its surface. Your feet age more slowly than your head. GPS satellites tick faster than ground clocks. Time also slows with velocity. Moving clocks tick more slowly than stationary ones. Muons from cosmic rays live longer when traveling near light speed. Particles in accelerators decay more slowly than particles at rest. Astronauts age imperceptibly less than people on Earth. These aren't corrections applied to defective clocks. Clocks work perfectly. They measure time accurately. It's time itself that varies. The rate at which physical processes occur, atomic oscillations, radioactive decay, biological aging, light, propagation, genuinely depends on motion and gravity. Einstein revealed this over a century ago through pure thought, guided by the principle that physics should look the same to all observers and that light speed is constant. From these simple premises, he derived a universe where time is relative, where space and time interweave, where gravity is geometry. Experiments confirmed his predictions. First, through astronomical observations, starlight bending near the Sun during eclipses, Mercury's orbital precession. Then through laboratory experiments, particle accelerators, atomic clocks on aircraft, ultra-precise optical clocks separated by centimeters. Each test strengthened confidence that Einstein's vision was correct. Now, a century later, general relativity is among the most thoroughly tested theories in physics. It passes every experimental challenge with remarkable precision. This success means we can trust its predictions beyond what we've tested directly. Black holes, predicted by general relativity, were confirmed through gravitational wave detection and direct imaging. The Big Bang, implied by applying general relativity to the universe's expansion, is supported by vast evidence. The theory makes our technological civilization possible. GPS, which billions use daily, depends entirely on relativity being correct. So do particle accelerators, where discoveries like the Higgs boson occurred. So will future technologies, quantum computers, gravitational wave astronomy, precision geodesy. But beyond practical applications, time dilation reveals something profound about reality's nature. Time isn't an absolute stage on which events unfold. It's part of the performance itself, shaped by mass and motion, variable across space. There's no universal now extending throughout the cosmos. Time is local, specific to particular world lines through curved space-time. Events simultaneous in one reference frame aren't simultaneous in another. Past, present, and future blend into a four-dimensional structure where position in time is as negotiable as position in space. Yet causality remains intact. Causes precede effects in all reference frames. Physical laws work consistently. The universe maintains coherence despite time's relativity. This coherence is perhaps the deepest mystery. How does nature arrange for physical laws to remain constant when time itself varies? How does space-time curvature produce gravity while preserving causality? How do quantum mechanics and relativity coexist despite their mathematical incompatibility? These questions drive current physics research. The quest to unify general relativity and quantum mechanics continues. Understanding what happens inside black holes, at the Big Bang singularity, at the Planck scale, these challenges await resolution. But what we know already is extraordinary. Time flows at different rates. This is established fact, measured precisely, confirmed extensively, applied routinely. The universe is genuinely stranger than our everyday intuitions suggest. Climb a mountain and you age faster. Travel in an airplane and you age more slowly. Stand near a massive object and time slows down. Move at high velocity and time slows down. These aren't thought experiments. They're measurable realities woven into the fabric of space-time itself. Einstein gave us the equations. Experiments confirmed the predictions. Technology applies the results. But the conceptual revolution remains stunning even a century later. Time is not what we thought it was. We live in a universe of relative time, where clocks disagree, where simultaneity is negotiable, where the rate of time's passage depends on where you are and how you move. This is simply how things are. The universe doesn't care about our intuitions. It operates according to its own logic, revealed through careful observation and deep thought. The logic is beautiful. Space and time form a unified structure. Mass, an energy curve that structure. Curvature affects how time flows and how objects move. Everything fits together elegantly, described by compact mathematical equations with profound implications. We inhabit a cosmos more wondrous than our ancestors could have imagined. Time itself is fluid, space-time is curved, gravity is geometry, and the universe expands, carrying galaxies outward into an unknowable future. Yet we can understand it. Not perfectly, not completely, but genuinely. Through patient observation, careful experiment, and creative thought, humans have decoded fundamental aspects of how reality operates. Time dilation is one such aspect. From GPS to atomic clocks to black holes, from your head aging faster than your feet to Earth's core being younger than its surface, this strange truth permeates existence. It's counterintuitive, it's verified, it's beautiful, and it's true. So when you look up at GPS satellites orbiting overhead, remember they're experiencing time differently than you are. When you climb a mountain, know that you're moving to where time flows faster. When you move quickly, understand that time itself slows for you. These aren't abstractions. They're realities, as genuine as the ground beneath your feet or the stars above your head. The universe revealed itself to be stranger and more elegant than expected, and we've learned to see it as it truly is. Time moves slower in space, but faster on mountains. Not because something is wrong with our clocks, but because that's how time actually works. This is the mystery of relativity, explained. Thank you for listening. If this journey through the nature of time spoke to you, consider subscribing to continue exploring the cosmos at a gentle pace. There are countless other mysteries waiting, each one revealing more about the extraordinary universe we inhabit. Until next time, may your time flow peacefully wherever it takes you.